Okay, welcome to this first session on the last day of NMR 2020. And it's my pleasure to welcome Francesca Toni. And let me say a few words about her. She's a professor in computational logic at the Imperial College in London. And there she is the leader of the group Computational Logic and Argumentation. And she's a very well-known person in the field of argumentation for quite some time. She holds a PhD from the Department of Computing, Imperial College London, and started her academic career at the University of Pisa in Italy. And she's been very active in the field of KR. She's a member of the steering committee of KR. And as far as I remember, she was PC co-chair of KR 2018, correct? Okay. Correct. And of course, she's very, very active in the community. Her current research focuses on argumentation in AI, argument mining, and explainable AI. And now you are, Francesca, you are bringing argumentation a bit more close, a bit closer again to non-monotonic reasoning. Thank you very much. And we are looking forward to the talk.
Thank you, Gabriele, for the kind words. And thanks to Vanina and Ivan for inviting me. It's a pleasure to be here. So I'm going to talk about computational argumentation for non-monotonic reasoning. Along the lines of kind of, non-monotonic reasoning. And computational argumentation indeed has its roots in non-monotonic reasoning. Indeed, starting from the late 1980s, it originated as a way to reconcile diversities across different non-monotonic reasoning formalisms. And we'll see a little bit more about that. And in particular, abstract argumentation and assumption-based argumentation, I will briefly talk about, have their roots within the non-monotonic reasoning tradition. Computational argumentation also has roots in other settings, in particular, in diffeasible reasoning, studied in philosophy, decision-making, and the work on resolving inconsistencies that all have played important roles in the development of the field and have contributed to some important contributions within the field of computational argumentation. But I will focus on the non-monotonic reasoning roots, if you like. So what I'm going to do in this brief talk is overview how several non-monotonic reasoning formalisms can be understood in terms of two formalisms for computational argumentation, namely abstract argumentation proposed by Zhong in '95 and assumption-based argumentation that dates back to 1997 with work by Andrei Bondarenko, Zhong himself, Kowalski, and myself. I will then, following up on Gabriele's introductions, focus a little bit or conclude the talk on how this work on computational argumentation has a role to play for explanation. And within this talk, I will focus on explanations for membership and non-membership in answer sets and other non-monotonic reasoning formalism, explanation for decisions, and explanations for the outcomes of case-based reasoning. This part will be somewhat orthogonal to a tutorial I'm giving this afternoon with Antonio Rago in KR, and also orthogonal to a talk that Guilherme Passos, one of my PhD students, will give at NMR later this afternoon. Okay, so let me start with an illustration of argumentation, computational argumentation for non-monotonic reasoning formalism, capturing non-monotonic reasoning formalism. Let me use a very simple, well-known example, the presumption of innocence. A person is innocent unless proven guilty, clear case of non-monotonic reasoning. So assuming that we know that Mary is a person accused of some crime, by applying this principle, should Mary be deemed innocent? And of course, the answer is yes. And you can use whichever formalism for NMR you like to represent reasoning with this principle, and you would get the same outcome. that yes, she should be deemed innocent. You can represent this in logic programming. Here, I stands for innocent, P for person, and G for guilty. That's how you would represent this, this with the use of a negationist failure. You could represent it in default logic and other monotonic reasoning formalism in a different way. You could represent in non-monotonic modal logic and other formalisms for non-monotonic reasoning in this other way. But at the end of the day, they will all give the same outcome, namely that innocent Mary should hold. Argumentatively, what is happening, no matter which formalism you're using, Mary is a person accused of some crime. There is an argument for Mary to be deemed innocent, let's call it I Mary, and there is no objection against this argument. Because there is no objection, then the argument can be deemed to be dialectically good, and Mary thus can be deemed to be innocent. Now, different formats for non-monotonic reasoning choose different ways to represent this argument and define the attack formally in a different way. But at the end of the day, that's what they're all doing. They are, kind of giving ways to construct an argument and no way to construct an attack against this argument. So if instead, and that's where the non-monotonicity comes to play a role, a reliable witness is accusing Mary, then non-monotonically, we would obtain an objection against the argument for Mary's innocence, and then no longer draw the conclusion that she's innocent and draw instead the conclusion that she's guilty. So that's where the kind of the non-monotonicity comes to play a role, and within all frameworks that I have listed on the previous page, we would obtain indeed this behavior. Of course, you can have much more involved debates about arguments, and as a further illustration, consider my policy for UK and European breakdown and recovery assistance with the nationwide building society in the UK. You can see, focusing on these two bits, that I am covered if I am traveling in a private car, but I'm not covered if the car is not registered to me, unless I am in the car. So there is a clear element of rules and exceptions embodied within this real life policy. So focusing on these two aspects of the policy, we could have a more involved debate about arguments, and in particular, assuming that Mary is an account holder traveling in a friend's car and the car breaks down, we can build an argument using the first bit of the policy for Mary being covered. She's traveling in a private car. We can build an objection based on this bit of the second bit of the policy. There is an objection because the car is not registered in Mary's name, and therefore she should not be covered. But then we can use the unless clause to build a further argument as an objection against the original, against the attack. So you can see that the debate can get involved, and at the end of the debate, there is nonetheless an evaluation of the dialectical goodness of the initial argument. So again, this example can be formulated in any non-monotonic reasoning formalism of your choice, and the behavior you would obtain with respect to any correct formulation will be the same, that Mary is covered. Okay, so the first formal way to accommodate and represent this process of argumentation is abstract argumentation by Zhong. An abstract argumentation framework, as you probably all know, is a pair consisting of a set of arguments and the binary relation of attack between arguments. We can visualize an argumentation framework as a graph, and the previous debate about the breakdown coverage can be represented by an argumentation framework with three arguments. So args has three elements, and that are indicated in blue in this graph. And the attack relation consists of two pairs. In Mary attacks NC Mary, NC stands for not covered, and NC Mary attacks C Mary, C stands for covered. I use a standard sum notation in what follows. In particular, the notion of attack between individual arguments can be lifted up to a relation of attack between sets of arguments, or hybrid between arguments and sets. So what do you do with this abstract argumentation framework? Well, there are semantics for them that help us determine what dialectically good conclusions one should draw from these frameworks. For example, that Mary is covered. These semantics are basically recipes that characterize these good sets of arguments, where sets of arguments are often referred to as extensions. There are various definitions. Here we have a partial list. The one that plays a role within this talk is that of, a main role within this talk is that of stability. So a set of arguments is deemed to be stable if it is conflict-free, which means it does not attack itself. And in addition, it attacks each and every argument that it does not contain. So this is a kind of way to establish what is good. And in this very simple example, the example we're seeing here, we have that NC Mary alone is conflict-free, but if you add C Mary to NC Mary, you get a non-conflict-free set, because there is a conflict within the elements of the set. And the set consisting of in Mary and C Mary is conflict-free and stable, because the only argument outside it is NC Mary, and it's attacked by elements in the set. And also, trivially, it is conflict-free. So if you put C Mary and in Mary, you have no conflicts within the set. This is just an example of semantics. There are, and this is just an illustration, there are other recipes. I'm not going to go into details and about the difference. What's important is that you can distinguish the two, the various semantics into two broad groups: credulous semantics that possibly sanction alternative sets as good extensions, or skeptical semantics that only identifying one good extension, taking absolutely no chance. Okay, so you can also have alternative presentations of these semantics rather than by extensions, which are sets of winning arguments, dialectically good arguments, I called them before. You can also characterize them by means of labellings, which are more fine-grained. So you can identify what's winning and also what is losing and what's undecided. Labellings are mappings from arguments to these three labels, different restrictions on these labellings amount to different semantics. So this is an equivalent way to formulate semantics. Okay, so you can use abstract argumentation to capture all the non-monotonic reasoning formalisms that we have mentioned. Not all, actually, some of the non-monotonic reasoning formalisms we have mentioned so far. Logic programming is an instance, for example. You need to choose which arguments and which attacks you want in order to instantiate the framework. And the arguments can be seen as deductions from the logic programming rules and negating kind of the negation exterior literals. The attacks amount to disagreeing on the negation exterior literals that support arguments. This is a simple example. We have got a logic program P if not Q, Q if not R, where not is negation exterior, and you can build an argument for P supported by not Q using this rule, and an argument for Q supported by not R using this other rule, and an argument for not P supported by itself. And then you would get that the black here argument attacks the kind of red one because it disagrees with the premise of the red one. So this provides an instance of abstract argumentation because I've chosen what arguments and attacks we obtain. And then you can apply whichever semantics of argumentation. This is the way to visualize some of the arguments here as a graph. You can then apply the semantics, the recipes for argumentation I've given you before, And by doing so, you can capture actually a bunch of existing semantics for logic programming. And that's what Zhong showed in his work in '95. So you can capture stable extension, you can capture answer sets by means of stable extension, as well as other semantics that I'm not going to go into detail. So it's an alternative, so argumentation provides an alternative of logic programming, and you can, and Zhong showed that you can also capture other semantics for logic programming, such as the completion, as well as Pollock's diffeasible logic and Reiter's default logic. And the semantics is the same as this, the one corresponding to answer sets in logic in kind of logic programming, but the arguments will be different. So you build the arguments using the default rules given, as well as first order logic. So the arguments are built differently, but the semantics of stable extension that default logic uses is the same semantics that logic programming uses under answer sets. Okay, so abstract argumentation is a very abstract kind of framework. For applying it, you need to choose the arguments and the attacks up front. And once you've chosen them, they're really black boxes. There are other forms of argumentation in computational argumentation, in particular structured argumentation. There are various formalisms in this category, and within all arguments and attacks are kind of obtained at runtime from building blocks that are specified in the underlying frameworks. There are several such approaches. There is diffeasible logic programming. Guillermo is in the audience, so I definitely want to mention that. There is ASPIC, ASPIC Plus, etc. There is deductive forms of argumentation, but I focus on assumption-based argumentation that I have contributed to in the past. So what is assumption-based argumentation? Here we provide the building blocks of arguments and attacks. These amount to deductive systems consisting of a language and a set of inference rules for building the arguments. Sets of assumptions, a set of assumptions that can be chosen to support arguments and that are the focus of attacks obtained by building arguments for the contrary of assumptions. So a contrary mapping is given as part of the specification of another framework. So then arguments are trees, which amount to deductions with respect to the underlying deductive systems and are supported by assumptions. And attacks are directed at the assumptions in the support of arguments by deriving their contrary. Very simple example, rules, I've got just two rules, S if B and T if C, three assumptions A, B, C, and I specify what the contrary of A is, contrary of B is, and contrary of C is. These sentences S, T, and U respectively. And U will be part of the language which is left implicit here. Then I can build amongst the arguments an argument for A supported by A, an argument for S supported by B using this inference rule, and an argument for T supported by C or using these inference rules. These arguments are all including in their support assumptions A, B, and C. Then I can build debates whereby the argument for T supported by C attacks the arguments for S supported by B because T is the contrary of B. And this in turn attacks the argument for A supported by A because the contrary of A is S. So you can see how you can obtain arguments and attacks automatically from the building block. Now, flat ABA is a specific type of ABA where there is no assumption in the head of the rules, and you can define semantics for flat ABA the same way as you do for abstract argumentation, talking about sets of arguments. But you can also in ABA talk about semantics in terms of sets of assumptions, which are the building blocks of arguments, equivalently. This is just an example, but we don't really have time to go into it. So what's important is that flat ABA and abstract argumentation are in one-to-one correspondence. So every flat ABA framework can be written as an abstract argumentation framework, and vice versa, every abstract argumentation framework can be written as a flat ABA framework. When you go to look at non-monotonic reasoning formalisms, they all accommodate and represent different kinds of arguments and attacks within ABA too. But the majority of what's out there deploys the same semantics of stable extensions. And this is how you would, a very simple example that illustrates how you would capture default logic and the presumption of innocence for default logic in ABA. You would specify that all the consistency assumptions are assumptions. And these are, premises of inference rule in the default rules, part of a default logic. So you would get that the assumption that John is reliable here attacks the assumption that Mary is not guilty, where assumptions here means it is consistent to assume that. So this is a specific instance of ABA. But it is basically boiling down to getting stable extensions as the semantics for default logic. So when you capture some of the non-monotonic reasoning formalisms out there, flat ABA is not enough. You need to go beyond flat ABA, and you have to allow for assumptions to be derivable by means of arguments using your inference rules. So for the breakdown assistance case, an autoepistemic logic formulation using a model operator L would amount to using as inference rule all the ones of classical logic for the underlying language, plus some domain-specific inference rules that would, for example, sanction that an account holder Mary is an account holder and is traveling in a private car C, and C is private, and you don't believe that she shouldn't be covered when traveling the car, then she's covered. So this is an example of kind of statement you would try to represent this setting in autoepistemic logic, and because to capture the semantics of autoepistemic logic by means of stable extension semantics for ABA, we need to consider all inference rules of classical logic. We get that from an inconsistency, you would derive everything, and thus assumptions can be derived. So you need a non-flat instance of ABA in this case. So the assumptions are trivially, in this case, positive and negative beliefs. And the contraries are defined as indicated here. So this is somewhat an overview of what computational argumentation can do for non-monotonic reasoning. It can basically capture it in different ways and following different formalisms, and can show that all these different formalisms have been defined in such a way that their semantics correspond to stable extension. So this is somewhat the reconciliation part of the landscape. Of course, the instantiation of these frameworks within computational argumentation means that other semantics that have been defined for argumentation, other than stable extensions, could be deployed for these particular instances. Rather than studying this, I'm going to now move on to the final part of the talk for the remaining, I think, 6 minutes that I have, and talk a little bit about how non-monotonic reasoning via computational argumentation can play a role within the explainable AI landscape to support definitions of explanations. So the first example I'm going to give you is about explaining another non-monotonic reasoning formalism, and this is answer set programming. In particular, you may want to ask why a certain literal is a member of an answer set of a consistent logic program, or why it is not. And intuitively, what we do is the explanation that we determine is based on the use of admissible dispute trees which are derived from computational argumentation for the arguments whose conclusion is the one we want to explain. And we consider two types of justification in this work, which is with Claudia Schulz, a former PhD student. We have the argument view, and for this we provide attack trees, or the literal view, for which we provide what we call, or what Claudia calls, labeled ABA-based answer-set justification. So for this kind of explanations, we use assumption-based argumentation as the underpinning, empowering, non-monotonic reasoning formalization for explanation. We also look at why a literal is not in an answer set in a similar way. Okay, just as an intuitive example, consider this rather simple and small answer set program, which has these two answer sets. And you've got to trust me in this. I'm not telling you why. This is what the answer sets are. Even in this very simple case, it is not at all trivial to see why D, for example, is a member of S1, or why A, for example, is not a member of S2. So you may believe, and I would agree, that answer set programming is fully transparent, and we can really understand by looking at the definition of answer sets what happens here. But even in such a small example, this requires quite a bit of thinking, and some guidance in terms of explanation is really very much needed. For larger answer set programs and larger answer sets, this becomes even more. So what kind of explanations can we generate by using computational argumentation? Well, one first type is that of attack trees, whereby we identify arguments for conclusions that we want to explain. So in this particular case, we want to explain why D is in S1, where S1 is this answer set, and this is our given answer set program again. So then we can say, well, D is in S1 because I can build an argument for D, which is supported by an assumption, not A, and no factual premise. So this is another component the arguments can have, and these are the facts that I use to derive a certain conclusion, where a fact could be E in this particular example. So this is an argument which is in favor of D being in the answer set. There is an argument against this argument, which is an argument, a negative one, because it's against, that would say that actually this not A is something which we can argue against. So indeed, we can prove, we can build an argument for the contrary of not A, which is not A. And this is an argument which is supported by assumption not C and not D. Each of these arguments comes from the use of some rules in the logic program that are treated as inference rules in ABA, and so on and so forth. So we can actually, and in this particular example, we can see that this counter argument against the initial one is defended against by the same initial one. So although this is if you like, an infinite debate, it just tells you why this is there, because D can admissibly defend itself against the one counter argument it has. So this is an example of the kind of explanation we would obtain in here. And as I said, we also have explanations in the form which are about literals rather than arguments. And this is a bird's eye view of what those are, but I don't have much time to go into detail. We also use ABA to explain decisions when these decisions are, in a sense, mapped by counterparts in ABA. So we have defined decision-making frameworks that have ABA counterparts to provide explanations. And in this case, again, we have debates as explanations between two fictional players, the proponent P, which labeled some of these boxes, and an opponent O, which labeled some other of these boxes. And we can extract the dialogical, conversational, linguistic explanation from these two trees. For example, the decision D2 is best according to a certain notion of kind of weak dominants here, as it meets two goals, G1 and G2, as identified by these defending arguments here, and also D8, which is a potential objection given by the opponents, and because it also meets goals G1 and G2, unnecessarily has attributes A9, which is somewhat pointing to non-minimality, whereas we're after minimally weakly dominant solutions here. You can see that this kind of linguistic explanation can be directly extracted from these dispute trees between proponents and opponents. And finally, we are using argumentation in the form of abstract argumentation here to explain the outcomes of case-based reasoning. Guilherme is going to give a talk this afternoon at NMR, so I'm not going to give you many details about this, but basically within the sceptical case-based reasoning, where you've got a bunch of past cases, a default outcome, and you want to determine the outcome of a new case, you can use abstract argumentation as a counterpart to explain predicted outcomes for new cases. And we have used actually this methodology in kind of collaboration with Thomson Reuters to explain the outcome of legislation in the UK Parliament, allowing to visualize the kind of debates that explain the outcomes, for example, as in this picture. To conclude, I have overviewed how abstract argumentation and assumption-based argumentation, two forms of computational argumentation, have their roots in and provide a unifying view of non-monotonic reasoning, at least some early approaches to non-monotonic reasoning, and how either and both can serve as the basis for explanation. Antonio and I, as I said, are giving a tutorial this afternoon in which we will overview other applications of computational argumentation for explanation. I thank you for your attention, and I'm happy to take questions.